Welcome, ladies and gentlemen, to our lecture on torque. In our last lecture, we discussed the rotational motion of rigid bodies, and we ended by introducing the idea of torque as a kind of rotational force. I'd like to discuss torque in a little more detail in this lecture. So we have torque applied when we have a force applied at some distance from an axis of rotation in a direction perpendicular to that distance. So if this is our axis of rotation pointing out of the page, so we're going to have things rotate around this way, and we have some distance out from here, and then we have a force applied like this, that will produce a torque. And remember that torque, tau, equals R cross F. So as I've drawn it here, the torque would point out of the page. We would get an angular acceleration that points out of the page, which means we get this counterclockwise rotation. Okay? So the effect of this cross product is to distill out just the perpendicular portion of the force, because that's what matters for torque. So you can imagine if I still have this axis, and I still have this distance r out from the axis, but instead, at the end here, I apply a force in this direction. Okay? Now, the angle between this force and this r is theta here. And we know from doing cross products that the magnitude of the cross product, r cross f, okay, the magnitude is equal to rf sine theta. But what is f sine theta? Well, if I go back over to my force here and I just look at the picture, I have the force pointed this way. I have the direction of r here. And then here, if this is theta, I would have f sine theta. So this f sine theta ends up just being the portion of the force that's perpendicular to this distance from the axis, okay, r. And it's this perpendicular component that creates torque, okay? So we see that torque depends on the force applied, right? So our magnitude of torque, actually let's write the magnitude is just without the harpoon, is RF sine theta, right? So it depends upon the force, okay? It depends on the direction that the force is applied, because the direction will indicate how big the perpendicular component is, right? It also depends upon the magnitude of the force, okay? How hard you push on something. And so if we have a wrench here around some bolt, and we're going to twist it this way, if we apply a force right here, if I can push on the wrench harder than you, then I can create more torque, right? But notice that the torque also depends on this length r, okay? Our distance from the axis of rotation. So if this is something like a wrench, and you can't push on it as hard as I can, you could still create a bigger torque if your wrench just has a longer handle, right? And so your application of torque, or your application of force, is way out here. You could potentially create a bigger torque than I could, even if you couldn't push on the handle as hard as I can, just by having a longer handle, okay? When I was a teenager, I had this really crappy old Volkswagen Beetle, okay? That was my car. And my dad and I had to work on that car all the time. And when we were working on that car, sometimes there was a bolt that we couldn't get to come loose, okay? Something was bolted on, and over the years, a little bit of rust accumulated or whatever, and we couldn't get the bolt to come loose. So do you know what we did? we actually grabbed this long metal pipe and we put it over the handle. Okay, so we have this big pipe. We put it over the handle and the pipe was really long. And then what we did is we pushed on it way out here. And what that did was allow us to put a greater torque on the bolt, and that let us unscrew a stuck bolt that neither of us could get undone. Okay? This worked because we're increasing R in this calculation of torque, right? We're making R longer, and that makes torque bigger. Okay? Oftentimes, when we got the pipe out, you actually could apply a lot less force and the bolt came undone really easily. Okay? This is a key point to understand about torque. The magnitude depends on both the tangential force applied and the distance from the axis of rotation to the point where the force is applied. Okay? So both R and F, as we've written it here, matter for the torque. Okay? They both affect the magnitude of the torque. It also means that torque is defined with reference to some axis of rotation. In this case, it was right here. Okay? We're rotating things around that axis of rotation. When we move the axis of rotation, we changed all the R's involved, right? If we have multiple torques involved, we change every R by changing the axis of rotation. Okay? We may also change the angle, theta, between R and F, depending on how we're moving the axis of rotation, right? So imagine if I have an axis of rotation here, I have a force applied here, there's some distance R between them, right? I could move the axis of rotation here and I'd have this new distance, right? D, we'll say. Okay? But I also could move the axis of rotation, say, up here, right? And then if my R moves this way, right? If this is my new R prime, then this angle changes, right? Now they're not perpendicular. Okay? So by moving the axis of rotation around, I actually change the torques involved, even if none of the forces involved changed. Okay? And we can often understand the impacts of torques by using Newton's laws, modified for rotational motion. Okay? And the most important of these, of course, is going to be Newton's second law, but modified for rotational interactions. So we have the sum of the torques, is equal to I alpha. Okay? The sum of the torques is equal to the moment of inertia times the angular acceleration. Okay? And we use this tool just like we used Newton's second law. Okay? We sum up all the torques, we set that equal to I alpha, and then we solve for whatever it is that we care about. Okay? Torque is a key physical concept to understand because it's all around us in the world. As an example of how torque is all over the place in the world around us, let's think for a second about balancing some object. We said in a prior lecture that we could do that by putting something directly below its center of mass. For example, if we had a ruler and we wanted to balance it on our finger, we'd put our finger right under the center of mass. Okay? What we're actually doing here is by putting our finger here, we're creating an axis of rotation right above our finger. Okay? And then to balance, what really has to happen is that there's no torque on the object, so there's no angular acceleration. Okay? So if we have each little piece of mass here of the ruler being pulled straight down by gravity, when we put our finger under the center of mass, we have the same amount of mass on either side of our finger. Okay? And this means that, say, on the left side, where this force is pulling down, we have some distance r to any given piece of mass, and this r cross F becomes r mg, right? And this one is, say, if we had a coordinate system like this, minus r times minus mg, so it's positive. On the other side over here, we have r, and now we have a positive r and a minus mg, so we get a minus r mg. And these torques, of course, the positive one gives us a torque counterclockwise, so using our right-hand rule in the positive direction, okay? And this one on the right side over here gives us this clockwise rotation, right? Negative in our right-hand system. And when these are the same, so when I add up all the masses over here, and I add up all the masses over here, what we end up with is that this term and this term are equal, and we get equals 0. And this means that our angular acceleration is 0, or that the ruler balances, okay? So our net torque in this case is 0, which means we have no angular acceleration. So now imagine instead that we have two big weights on either end of, say, a massless ruler. Now, if we have some axis of rotation, then for macroscopic objects like this weight, each little piece of this weight would apply its own torque, right? Because the distance r from the axis of rotation is going to be different for every little piece of the object. But we can correctly account for this effect by assuming that all of the mass of the object is located at the center of mass of the object, okay? So if we say instead we treat it as if all of the mass were at the point where the center of mass is, it actually works out correctly. And so the distance from the axis of rotation for this whole object then is this distance. We'll call this m1, we'll call this r1, and then for this other object, it's r2, and this is m2. And this is for an axis of rotation that's right here, okay? We haven't really defined where it is. It's just wherever from object 1, it's whatever this length r1 is, okay? Now you can see that to balance this, I would need m1 g r1 plus m1 g r2 equals 0. And we can see that, noting that m1g points this way, m2g points this way, and then r2 points this way, and r1 points this other way, we can see that these are going to have opposite signs, okay? So these two torques are going to have opposite signs, so there's going to be a minus between them. So in other words, what I need for this to balance is for m1g r1 to equal this should have been a 2, to equal m2g r2, okay? And this makes intuitive sense, right? If I want this to balance, I need the torque on either side to be the same. This will result in an angular acceleration of 0 because it'll have a net torque of 0. So that means that if m1 equals m2, then it must be the case that r1 equals r2, right? So then our balance point, the point where we create an axis of rotation, should be right in the middle. But what if m1 is not equal to m2? In that case, we have this distance m1 and r1, and we can see that we have some distance between the center of masses of the objects, d. Okay? So what I want is for the torque on either side to be the same. So I want m1 g r1 to equal m2 g r2, okay, we see that the g's can cancel, so we can stop writing the g's. And we can replace r2. Okay, so m1 r1 equals m2. And if we look at this picture, you see that r2 is d minus r1. Okay, so d minus r1. Then I can just solve for here. And what I get is that r1 equals m2 times d over m1 plus m2. And we can see what our new axis of rotation needs to be, where it needs to be placed for the torques to equal 0 on this and for us to have no angular acceleration. Okay? And you can see from this that if I make m2 bigger, then I move the balance point toward m2. Okay? By the same token, if I make m1 bigger, we can see in my equation that I'll move the balance point this other way toward m1, right? And this makes intuitive sense to us. And it makes intuitive sense because we see it in the world all the time, okay? We're exposed to it all the time. So if we want to make something balance, we need to find an axis of rotation that puts equal torque on either side of that axis. And the location of that axis is going to be closer to the side with more mass, okay? If we have some object that's not that doesn't have kind of uniformly distributed mass, okay? So this is how our balancing trick with the center of mass is actually working. By putting something directly under the center of mass of the object, we're creating a situation in which gravity applies a torque of opposite direction but equal magnitude to an axis of rotation directly above our balance point, okay, which is at the center of mass. So now let's look at a really common simple machine for a second. Let's look at the lever. A lever works very similarly to what we just talked about with balance, okay? We have a rod or a plank of some kind, and we have a fulcrum, okay? And a fulcrum is just an object that we put under the rod or plank to press on it so that we have an axis of rotation right above that fulcrum, okay? So imagine I have some heavy object that I can't pick up, okay? But I can wedge a plank under it. So imagine I get a plank under it like this. And then I manage to get a rock or something to use as a fulcrum under the plank, okay? I can position this fulcrum so that it's closer to the heavy object than the other end of the plank, right? So that this distance x is shorter than this distance d. Okay? Then I could potentially use, say, my weight on the other end. And even if the object weighs more than me, I can potentially move it by taking advantage of the fact that d is greater than x. Okay? So, just as an example, let's say that this m is equal to 5 times my mass. Then what I want to do with this is have the torque on this side be greater than the opposite torque that this object applies to this side. Okay? So I want mgd to be greater than mgx. Okay? That's going to mean that my object has some angular acceleration after this. Okay? So what does that mean? It means that mgd is greater than 5 mgx, and then canceling all the similar terms, it means that d has to be greater than 5 times x. Okay? So if I want to move an object that weighs 5 times what I weigh, I can create this lever system, and I can just make D over here, this length, 5 times the length of this length. Okay? This X that I drew before, I should have drawn it to the center of mass, right? Because our force is the weight of the object. So let's make it a little more clear. My plank is here, my object is like this, so X should have been like this far, right? But everything else still holds. That was just an inaccuracy in the drawing here. What I need is for my center of mass to be this distance D away from the axis of rotation, the object's center of mass to be X, this distance away from the axis of rotation, and then if the object has a mass 5 times my mass, I just need D to be at least 5 times X to move it. Okay? And we see levers pop up in a lot of physical systems because they're so simple to create and they're such a useful tool. So one example of a place where levers become really important is with our bodies. Okay? Our bodies are moved by muscles, and muscles can only contract. That's all they do. They're just tissue in your body that can contract. It can make itself shorter. So if we think of a simple joint like your elbow, okay? This is an elbow bone. Okay, so your upper arm is up here, and this is your lower arm down here. Okay? So your bicep is attached up here somewhere. And then it comes down and attaches to this bone. Okay? And all it can do is contract, which means it applies a tension force like this. Okay? So we'll call that F sub C, the force of the contraction. Now you can see that if your elbow is the axis of rotation, because this whole bone is going to rotate around the elbow, then this distance here, X, is going to define the torque, right? And this angle here, theta, is what we're going to use in our cross product, right? And the torque that your bicep can apply is the force of the contraction times the distance from the axis of rotation in your elbow to the point where the muscle's attached, sine theta. And you can see if this is your arm, and this is the bicep attaching, okay? And these are the bones in here, and you get the axis of rotation back here. That this angle theta is changing all the time, right? When my arm is basically straight, then this muscle is nearly straight, and the theta is really small, so I get a really small torque, right? For the same force of contraction. When my arm is bent almost all the way, then the bicep is attaching across like this, and I get a much bigger theta, okay? Here's the axis of rotation in my elbow, and I get a bigger theta, okay? So the torque that my bicep can apply is changing all the time because the angle that it's pulling at is changing all the time, okay? But now imagine I have a heavy weight in my hand. So my arm goes down like this. I have this out here. I'm just going to put a circle for my hand. And I have a big heavy weight in my hand. Okay? Now the weight is pulled down by the force of gravity, right? We'll call that mg, the mass of the weight times little g. And the axis of rotation is in my elbow somewhere. And there's this distance R, the length of like my forearm, right? And you can see that if I compare that to, say, where the bicep inserts, there's a lot more torque created by the weight than what the force of contraction of the bicep would create, right? So the muscle has to pull with a much greater force than the weight of the weight in order for your arm to bend, because the torques applied, the torque from the bicep here and the torque applied by the weight over here, are using such different distances from the axis of rotation. Okay? But notice also that as my arm changes angle, as my elbow changes angle, so for example, if this is my arm and the weight is in my hand hanging straight down, then the torque applied by the weight on my elbow, say the axis of rotation for my elbow is here, is 0, right? Because the weight is now pulling straight down like this, mg, and the angle between r, pointing this way, and mg is 0, okay? So theta equals 0, therefore, the torque from this weight equals 0, okay? But then as I bend my arm, so now I have this, I have my elbow here, and my arm's bent like this, and the weight's here. And this is pulling straight down like this. You can see that the angle between R and mg is changing all the time, right? And so then as my arm bends even more, like this, now mg points straight down like this. And this R is perpendicular to mg now. And then if we go a step further up here, and my arm is bent now like this, with this weight in it, we can see that R with mg pointed straight down, now it's less than 90, right? And so as I go through this motion of trying to bend my elbow with some kind of mass in my hand, the torque on my arm is changing all the time. And the torque that my muscle applies, the bicep muscle applies, has to be at least the torque of whatever's in my hand in order for my arm to bend, right? In order for the angular acceleration to cause rotation in this direction, right? So if you've ever lifted weights, you may have noticed that different sections of a given lift, like a bicep curl in this example, feel harder or easier, right? That's a real effect, and it's due to the changing torques involved as we move things around and we change these angles that are pertinent to the motion, okay? The angle that the muscle is making with the with this lever arm on the axis of rotation, okay? The angle that the weight is making with the lever arm on the axis of rotation, right? And these two things are both changing all the time. So you can see that when my arm is vertical, the bicep doesn't have to do anything. And indeed, I can let a weight hang in my arms and let the bicep just rest, right? And then as I bend my arm, the bicep has to do more and more. And when I get to this point, where my lower arm is perpendicular to the ground, it's completely horizontal, that's the point at which the weight pulls the hardest on my arm, right? Because this R is a fixed length. It's the length of my lower arm here. And the mg and the R are perpendicular in this picture, right? And then as I go up past that, the mg and the R are no longer perpendicular, which means that this torque, right, this was torque, isn't at its maximum value. Okay? Your entire musculoskeletal system works by applying torques on your body, and the motion of the human body can therefore all be understood through this lens. Understanding torques is key to understanding the physical world, and we see torques applied all around us all the time. It's even a key concept to understanding the motion of our body, as we've just shown. In the next lecture, we'll expand from torque to consider angular kinetic energy and angular momentum.